Hi, morning. Math 226, vector calculus. So we're using this Pearson MyLab system, which I suspect many of you have already used, but I haven't, so I'm learning how to use it for the first time. So how many of you have been able to log into the system? Or is there some kind of code you need to get into the MyLab for vector calculus? I know Alex Amin had a problem, but does anyone else have an issue with this?
Yes.
So what is it that you're missing?
Yeah, it's asking for the class code.
Sorry?
Class
Oh, you need
code.
a class code. Okay, and where do you usually get this?
I don't know.
Usually it's the professor gets it, I guess from the department or something, usually. They get the code, and then once you get the code, then we just have to pay for the online textbook, and then we get access to the class.
Right, and if you've used this system for Math 175 or 176, do you pay for it each time, or once you pay for it, do you have it for the whole
You have
calculus?
You have it for the whole semester once you pay for it, like the textbook and all the assignments and
So
stuff.
if you do this for Calc 1, you have to pay a second time for Calc 2.
Yeah, like for each different course, you have to pay a separate time for each,
Right.
textbook.
How much is it?
It's not too expensive. It's like usually like $60 to $70 usually. It's always less than 100 for the online class.
Right. So I guess the alternative would be when we didn't use MyLab at all, if you were at Lehman for the whole calculus sequence, you bought the textbook for Math 175, and then you used it for Math 176 and Math 226. So if it cost $100 for the textbook, since you were using it over 3 semesters, you save money. But it doesn't work that way with MyLab, evidently. Okay, so I'm making a note that I need a class code, and I will, as soon as we get offline today, contact the department or ask the department chair where it is and how I get it and how I send it to all of you. But so I assume once I get it, if I go on to Blackboard and just email you the class code, everyone will get it right away.
Yeah, that'll work. That's it.
Right, I mean, is that the only way to get it? Is it, is there an alternative method?
Well, I'm online and it says that to enroll in a course for the online textbook, you either need the course ID, right? Which it's not just like Math 226, it's like its own unique code per, like instructor. You either need the course ID or an invite link, which you'll probably get from the department.
And the course ID is not the number that you see on Blackboard next to the course.
No, it's something different. It's its
Okay.
own unique thing.
Well, I mean, but if there were 5 different sections of Math 226 at Lehman this semester, each would have a separate number.
The course ID, I think it's like just per instructor. Each instructor has a different one, and for like each class, I would say. But what's it? I don't know exactly like how the codes differ, but I just know that they're different for each
Right.
professor.
Yeah, okay. All right, so I will definitely figure that out. So more people are logging in, which is nice. So among the people who've just logged in, have any of you had access to the MyLab website for this class? Okay. So you haven't even seen the textbook yet. So maybe what I will do, so of course, I already put up 2 lectures covering the first 2 sections of chapter 13, which is what our, which is the beginning part of this class. So at least you have that, but you know what? Hang on one second. I'm going to go look at go to the My Lab, because I'm certainly on there, and see if there's something that's there that I can give you. Okay, so I found something in My Lab, and I'm going to, so it has the following. It says course ID. And what it says is Nathanson 54996. So if you could try that right now, if it's possible, see if that works. Nathanson 54996.
I just tried the code and it says your instructor's course is not accepting registrations. Contact your instructor.
Huh.
Yeah, I
Okay.
don't know about that. I think you probably have to talk to the department.
Right.
It's not letting us just enroll.
Right. Okay. Did any of you have a chance to look at either of the first 2 lectures that are on YouTube? Do you have any questions? So this is about vectors in 2 dimensions and vectors in 3 dimensions. Maybe just so we have something useful done today. I'll just say a little bit about that right now as kind of a review. And I don't know to what extent you have come across this in previous mathematics classes. Let me take a look at what I can do. So now you should see a nice white piece of paper that I can write on. Vector calculus. And we're looking at, I believe it is chapter 13, which is 2-dimensional and 3-dimensional vectors. And what is probably the very first section is 2-dimensional vectors. So now we're just working in the ordinary XY plane. And if you have a point P and a point Q, the vector from P to Q, you can draw this as an arrow from P to Q. So this is the head of the arrow. That's the tail. And we write this vector as PQ with an arrow over it. And this is different from the vector, if you were to go in the opposite direction, this is P and this is Q, the vector from Q to P goes from Q to P. And we would write that as QP. So now Q is the tail and P is the head. So between any 2 points, P and Q in the plane, any 2 different points, there's a vector from P to Q, and then there's a vector in the exact opposite direction and parallel, but pointing in the opposite way from Q to P. And what really matters is not so much the points P and Q, the start and stop or tail and head of the vector. What matters is the direction of the vector and the length of the vector. So if I take a vector, say from 0 to some point over here, if this vector is parallel to this and the same length and in the same direction, then we say these are equal vectors. So the vector is really, so there are 2 notions of vector. There's like a vector that's located in the plane between 2 particular points, but 2 equal vectors are simply vectors that have the same length in the same direction. And there's a way to represent vectors as coordinates. If P has coordinates x1, y1, and Q has coordinates x2, y2, then the vector from P to Q is, actually, you can think of this if you had a triangle, a right triangle. So the distance from here to here horizontally is x2 minus x1. And the difference from here to here vertically is y2 minus y1. So in coordinates, we would say the vector PQ has these coordinates. This is exactly, if you took the vector whose tail was at the origin and whose head was at this point, x2 minus x1, y2 minus y1. Right? So associated to every point in the plane, you have the vector from the origin to that point. But that vector could be translated from here to here, let's say. But a vector in the plane is just an arrow, has a head and a tail, a starting point and an ending point. And in coordinates, you write every vector as an ordered pair x, y. And you think of this as the vectors, the arrow starting at the origin and going to this point x, y in the plane. Okay. And there's a very simple arithmetic of vectors. You can add them, you can subtract them. Unfortunately or unfortunately, you can't multiply them. So suppose you have 2 vectors in the plane. So here's the plane. And here are 2 vectors. So let's call this vector V and this vector W. And we wanted to define vector addition. So there are 2 equivalent ways to do that. If you have these 2 vectors whose origins, if the origin is the tail, you can think of these as 2 sides of a parallelogram and just fill out the parallelogram. So this is parallel to this, and this is parallel to this. And then if you take the diagonal to the opposite end of the parallelogram, this is the sum of the 2 vectors. So this is sometimes called the parallelogram rule or law of vector addition. If you take in any physics, for example, where you study forces act like vectors, and they always draw these pictures to show you how you add forces in elementary physics. So this is the parallelogram rule. Alternatively, there's what's sometimes called the triangle rule, but it's the same thing. Here you take the vector V, then you take W and you translate it here. So this vector is parallel and equal to this vector. And then you form the triangle. and you get V plus W. So there's also the triangle law, if you like, or really law is not the right word, maybe method or picture, but that's how you add vectors. So for example, if you're in the plane, and you have the vector 4, 1, so V is the vector 4, 1, and let's say W is the vector 1, 2. What happens when you add these vectors? Well, in fact, V plus W is exactly what you get when you take the sum of the coordinates. So 4, 1 plus 1, 2. So you add the 4 and the 1, you add the 1 and the 2, and you get 5, 3. I mean, actually, if you draw your picture carefully, you see the same thing, because let's say here is 0, 0. Here is 4, 1. So you've gone over 4 and up 1. And then you want to draw this vector parallel with the tail right here. In this vector, you're going over 1 and up 2. You go over 1 and up 2, and you're exactly at the point 5, 3. So either from the triangle method or the parallelogram picture, you get the same point. But really, the fundamental fact is that algebraically, all you're doing is adding coordinates. And you don't have to draw the pictures. If you had the vector 73 minus 29, and you're adding the vector 111, 109, and 38, you add coordinates. 73 plus 109 minus 29 plus 38. When you add these, I think you get 182 and 9. And you can draw it if you like, but the sum of the two vectors is this. So vector addition is done by adding coordinates. Vector subtraction, just as you might expect, is what you get by subtracting coordinates. But I can draw a picture to, if you like, justify this, vector subtraction. So suppose we want to define the vectors V minus W. So you're given vectors V and W, you want to define the difference. So you might say, well, what should this be? It should be that if you start with the vector W and you add V minus W, you get V. That is, V minus W should be what you add to W to get V. So let's say here's the vector V, and here's the vector W. What is it that you would add to W? Let me draw this a little bit better, so make it a little more interesting. So what is it that you would add to W to get V? What vector? It would be a vector that looks like this, right? So if you have V and you add this, if you have W and you add this, you get V. So this should be, this vector should be V minus W. So let's just write it like this for fun. Suppose V has coordinates x1, y1, and W has coordinates x2, y2. And we want to satisfy the equation W plus V minus W equals V. So suppose this has coordinates, well, what did I say? x2, y2. Let's say this has coordinates z1, let's say x3, y3, and this has coordinates x1, y1. So we want this plus this to equal this, which means but what is this plus this? You add coordinates, you get x2 plus x3, y2 plus y3 equals x1, y1. But vectors are equal if they have the same coordinates. So x2 plus x3 has to equal y1, and y2 plus y has to equal x1, and y2 plus y3 has to equal y1. And if you solve for x3 and y3, x3 is x1 minus x2, and y3 is y1 minus y2. So what we're saying is, if you take the vector v minus w, that's going to have coordinates x1 minus x2, y1 minus y2. That is x1, y1 minus x2, y2. When you take it two vectors and you subtract them, you're just subtracting the coordinates. So maybe that's a little bit too complicated an explanation, but the takeaway is the same. What you have to remember is you add vectors in the plane by adding their coordinates, and you subtract vectors by subtracting their coordinates. So if you had the vector 7, 19, and you want to subtract the vector 22, 11, that's going to be the vector. You subtract the x coordinates, you subtract the y coordinates, you get minus 15, 8, right? Because 7 minus 22, I think, is minus 15. And 19 minus 11 is 8. Okay. Any questions about this? Again, this is really just what's in section 13.1, and I already talked about that in a lecture that's awesome. What else can you do to a vector? We can add and subtract them. I said you can't multiply them, but you can stretch them. So suppose this is the vector v, we can stretch it and get a longer vector. Or we could sort of like stretch it in the negative direction. If this is v, this is sort of like minus v. In fact, that is exactly minus v. Let me just sort of point this out. So here's the vector v, which has coordinates x, y. What would minus v be? It'll have coordinates minus x, minus y. So it's a vector that looks like it has the same length, but it's in the opposite direction. In general, if you take a number c, and when you're talking about vectors, another name for a number is a scalar. So scalar just means number in vector calculus. You can multiply a vector by a scalar. Suppose you take a scalar c. Let's say it's positive. Then we can define c times the vector v. So this is c times the vector whose coordinates are x, y. And we get a vector obtained by multiplying each coordinate by c. So the first coordinate will be c times x. Second coordinate will be c times y. So this operation is called scalar multiplication. We're not multiplying two vectors, but we're multiplying one vector by one scalar. And this works whether C is positive or 0 or negative. If C is 0, we just get the vector whose coordinates are 0. That's the origin in the plane. That's the 0 vector. If C is positive, you get a vector stretched in the same direction. If C is negative, you get a vector stretched in the opposite direction. So that's scalar multiplication. So for example, if I take the vector 2, 1, if V is the vector 2, 1, 2 times V is the vector 4, 2. So this is V, and this is 2 times V. V is 2, 1, this is 4, 2. Minus V means minus 1 times V. It's multiplying the vector by the scalar minus 1. So that's minus 1 times xy, which is minus x minus y. So if V is 2, 1, this would be minus 2 minus 1. That would be minus V. And minus 2 times V, that's minus 2 times 2, 1. That's minus 4 minus 2. So this is minus 2V. Right. So these are the simple pictures about vectors in the plane. There is a notion of the length of a vector or the magnitude of a vector. So here we have the vector V equal to xy, those are its coordinates. So this point would be x0, this point would be 0, y. How will we reasonably define the length of this vector? Well, if you look at this vector, it's the hypotenuse of this right triangle. In this right triangle, the base is x and the altitude or the height is y. And what does the Pythagorean theorem say? It says the length of the hypotenuse is the square root of the sum of the squares of the legs in a right triangle. So we define the length of V, these double arrows. Sometimes you use a single arrow, sometimes a double arrow. This is the length of the vector V is the square root of x squared plus y squared. So for example,
Professor,
yeah,
can you please explain where you have the coordinate to be 0, 0?
yes. So in the tail, the vector is 0, 0. The vector is the vector xy. Yeah. So that's the length of the vector. So for example, if this were the vector 3, 4, or the way I've drawn it, 4, 3, then the length, so the length of the vector 4, 3 is the square root of 4 squared plus 3 squared, which is the square root of 25, which is 5. Now, the more general situation is you have a vector from a point P to a point Q. And suppose P has coordinates x1, y1, and Q has coordinates x2, y2. And we want to define the length of the vector from P to Q. So again, we can think of this as the hypotenuse of a right triangle. This is x1, this is x2. So this distance from here to here is x2 minus x1. This height is y1, this height is y2. So the length of this leg of the right triangle is y2 minus y1. So again, we have a right triangle whose legs have lengths x2 minus x1 and y2 minus y1 respectively. By the Pythagorean theorem, the length of the vector is the square root of the sum of the squares of these differences, x2 minus x1 squared plus y2 minus y1 squared. So that's the classical formula for the distance between 2 points in the plane, or the distance for the vector from one point P to another point Q in the plane. So for example, if P had coordinates 3, minus 7, and Q had coordinates 5, 2, then the vector from P to Q, well, first of all, what is the vector from P to Q? Its coordinates would be 5 minus 3, 2 minus 7, which is 2, 9. Right? 3 minus 7, 5, 2. The vector from P to Q has coordinates 5 minus 3, 2 plus 7. So the length of the vector from P to Q is the square root of 2 squared plus 9 squared. So that's the square root of 85. Notice the length doesn't matter, doesn't change if you go look at the vector from P to Q or from Q to P. If you take the vector QP, its coordinates are going to be 5, its coordinates are going to be 3 minus 5, minus 7 minus 2. So that's minus 2 minus 9. And again, the length of QP will be the square root of minus 2 squared plus minus 9 squared, and that still is 85. Because again, if you look at the vector from P to Q and the vector from Q to P, they're pointing in opposite directions, but the absolute value or the magnitude or the length of the vector doesn't change. Okay, let's see. Let me just take a look at our textbook again.
Professor,
Yeah,
hi. Just to be sure, so since these videos are pre-recorded, are you gonna share in the Blackboard later on so we can like go over with them, or?
I'm sorry. What is it that you're asking?
Oh, the videos are pre-recorded, so are you gonna share it to Blackboard later on?
No. Everything is posted on the YouTube channel for this class.
Okay.
Right.
Okay.
So the first two lectures on sections 13.1 and 13.2, I posted last week. And the Zoom classes I also record and post, but it's all on that same YouTube channel.
Okay.
Okay.
Okay. Thank you.
All right. Let's see. Why? I need to make sure I can get into my lab. Good. Okay, let me see if I can share the screen with this. Okay, so I hope you can all see the text. So this is chapter 13. And section 13.1 is what I posted already on Blackboard, sorry, on Zoom, and have been discussing today. So these are just basic vector operations. Vector addition and subtraction. They're better pictures here, but it's all the same. This is so here is adding two vectors. This is what it calls the triangle rule and the parallelogram rule, but of course you get exactly the same vector in both cases. This is vector subtraction. You have vectors u and v, and if you start with v and you add u minus v, then you're supposed to get u. So v, u minus v, when you add them, you get u. That's geometrically what the difference of two vectors looks like. The magnitude of the length of the vector, so they're using single lines, so I will from now on, just like absolute value. But if you take 2 points P and Q in the plane, the distance between them, or the length of the vector between them, is the square root of the sum of the squares of the coordinates. That's what it is. So this is just summarizing the rule for how you add, subtract, and scalar multiply vectors. Yeah, there's one other thing I should mention, because it's at the very end of this chapter, I think, end of this section. Let me see if there's anything else. Okay. So if you have a vector v with coordinates v1, v2, then the length of v is the square root of v1 squared plus v2 squared. And we say that v is a unit vector if its length is 1. So unit means 1. A unit vector is a vector of length 1. And the simplest unit vectors in the plane, if you take the vector 1, 0, just go 1 unit horizontally, that is always written as the vector I. So I is the unit vector in the positive x direction. And if you take the unit vector 0, 1, which is a unit vector in the positive y direction, that's equal to j. That's the notation. So I and j are the standard unit vectors in the plane. And if you take any vector, like here's a vector, 3, 2. You write 3, 2, you can always express it in terms of these standard unit vectors. So you can always write 3, 2 as 3, 0 plus 0, 2, right? If you add these two vectors, you get 3, 2. But 3, 0 is like 3 times the vector 1, 0. Take the vector 1, 0 and scalar multiply it by 3, you get 3, 0. And 0, 2 is 2 times the vector 0, 1. But this is the vector I, and this is the vector j. So you can write this vector as this combination of a scalar multiple of I and a scalar multiple of j. And this number is sometimes called the component. Let's say this is the vector v. This is the component of v in the x direction. And 2 would be the component of v in the y direction. But you can always decompose your vector into, in the plane, as a scalar multiple of I and a scalar multiple of j. Okay, well, most courses start slowly, and this is no exception. So the first lesson in the syllabus is just vectors in the plane, and that's what we've been talking about. And so I will, this is recorded, I will post this on YouTube, and then I will immediately get in touch with the department to find out what I need to do so you can log into the course on MyLab. Right? Any questions before we go? If not,
No, it's
you-
pretty clear.
okay.
You said that he's gonna send the class access code.
As soon as I get the
Blackboard.
access code, I will email it to everyone and also post it as an announcement on Blackboard.
All right.
All right, so hopefully someone will get back to me today.
Professor,
Okay. Okay, be well, all.
Professor, one question now.
Yes, sir.
How is the grade for the class is going to be? The grade,
How is it
Quiz.
graded?
grade, exam, quiz, homework, any percentage ready for that?
I thought I already posted that on under course information.
I don't know that.
You know, how much is there are 4 exams and homework. But I'll double check how that, if I haven't posted that, I will post it. But, you know, typically, you know, your grade is a combination of your exam grades, and then there's some number of points also for the homeworks that you've done.
Thank you.
Sure. Any other questions? Okay. Then that's it for today.
Professor, I have a question. When it comes for the homeworks and the tests, like I know that like my math lab is like, because I've taken classes on it before, like it's very like to the point. If you don't get like the right exact number, they'll mark it as wrong. Will you go through like some of like the homeworks or like some of the exams, and like if we're close to the answer, you'll give us partial credit or something?
I'll see how it goes using the MyLab system. And if I feel like I have to go through things more carefully and give partial credit, I will. But there is a general principle in mathematics, especially in courses that are basically computational, where it's not like higher level courses where you have to prove theorems, that you're supposed to get the right answer, right? I mean,
Yeah.
So,
But
and
what
I
happens if we don't
they
get the
give
right
you
answer?
multiple, they give you, you know, multiple chances, I believe, on the homeworks to, like, if your first answer is wrong, they tell you and they give you a chance to correct it.
Yeah, the homeworks, I know that they do that, but mostly regarding in the test, I would say. Cause like I know in like the test, like if like you put like 1 decimal point, or like maybe you add like an accidental like space in my math lab, sometimes like they're very brutal when it's like no points at all.
Yeah. So when I give the first exam, which is in a couple of weeks, I'll go through it carefully and just see how it works.
Okay, thank you.
Okay. Okay. Be well all.